In the last video, we saw the definition of Bessel functions of the first kind of order nu and negative nu, respectively. And as long as nu is not an integer, then the general solution to Bessel's equation that we saw in the previous video is y equals c1 j sub nu of x plus c2 j sub negative nu of x. If nu is a non-integer, then the function y sub nu of x, which is the cosine of nu x times j sub nu of x minus j sub negative nu of x, all divided by the sine of nu pi, is linearly independent with j sub nu of x. If nu is an integer, then j sub nu and j sub negative nu are linearly dependent. We can't actually have nu equal an integer because the denominator of y is sine of nu pi. Any integer would zero out the denominator. But using a limiting process, as nu goes to m, where m is an integer, we can define the function y sub nu in the event that nu is an integer. Then since j sub nu and j sub negative nu are linearly dependent if nu is an integer, in that case, we have as our general solution y is equal to c sub 1 j sub nu of x plus c sub 2 y sub nu of x. Let's just see what this looks like here. We have our differential equation x squared y double prime plus xy prime plus the quantity of x squared minus 1y is equal to 0. Since we have x squared minus 1, we can see that nu is equal to plus or minus 1. Since those are integers, our general solution is y is equal to c1 j sub 1 of x plus c2 y sub 1 of x, and that y is there because nu was an integer. In the equations that we've looked at so far here, in the parentheses where we have the x squared minus nu squared, the coefficient of x squared has been 1. If that coefficient is some other number, say alpha squared, then a substitution can show us that the argument inside of the Bessel function, nu, j sub nu, becomes alpha x, and then y sub nu has an argument of alpha x. And that equation is called a parametric Bessel equation of order nu. And this may be bad form, but I'm going to go back up here because I forgot to say that this y sub nu is a Bessel function of the second kind. Now, if in the y term, instead of having x squared minus nu squared or alpha squared x squared minus nu squared, we have a negative in front of the set of parentheses and x squared plus nu squared. This is called a modified Bessel equation of order nu. A substitution involving the imaginary number I gives us the modified Bessel function of the first kind of order nu. It's denoted using I sub nu, and it's just j sub nu with ix in the argument, and the whole thing's multiplied by I to the negative nu. If nu is not an integer, then as before, we have a general solution of the modified Bessel equation, which is y equals c1 I sub nu of x plus c2 I sub negative nu of x. The modified Bessel function of the second kind is denoted by k sub nu of x, and it is pi over 2 times I sub negative nu of x minus I sub nu of x divided by sine of nu times pi. So again, we can't have an integer in place of nu, but a limiting process will let us define y sub nu of x in the case that nu is an integer. And then our general solution when nu is an integer is y is c1 I sub nu of x plus c2 k sub nu of x. And again, in the event that there's some coefficient of x squared that's different from 1, as we saw before with alpha x with j and y, we can see an alpha x in I and k. And all of that's described here. As a summary, for a non-integer real number nu, we would say that y is equal to c1 j sub nu of x plus c2j sub negative nu of x. If we have an integer real number nu or a parametric form of Bessel's equation, then our solution is c1j sub nu of x plus c2y sub nu of x. In the case that we have a non-integer imaginary nu, I know that's a bad form because an imaginary number is not an integer, but you know what I mean. Then c1 times I sub nu of x plus c2 times I sub negative nu of x is our answer, our solution. In the case that we have an integer, let's say an integer coefficient on the imaginary nu, or again, a parametric form of Bessel's equation, then our solution is c1 I sub nu of x plus c2 k sub nu of x. And now we'll just see what this looks like in practice here. We have the differential equation x squared y double prime plus xy prime. Hey, that's Cauchy-Euler-esque. Minus the quantity of 2x squared plus 64 times y is equal to 0. Because we have 2x squared, we can identify alpha as the square root of 2. We don't bother with the negative because the negative would just get washed out in our work. And nu, because we have this plus 64 in here, nu is equal to plus or minus 8i. So we've got a parametric form of Bessel's equation, and we have an imaginary nu that has an integer coefficient of 8. Y is then equal to c1 times I sub 8 of the square root of 2x plus c2 times k sub 8 of the square root of 2 times x. And that's it. There's just a lot that is represented by these symbols I and k. Moving on, the general solution to y double prime plus 1 minus 2a over x y prime plus b squared c squared x to the 2c minus 2 plus a squared minus p squared c squared x over x squared, all that times y is equal to 0. That's an equation. Okay, great. The solution is y is equal to x to the a c1j sub p of bx to the c plus c2 y sub p bx to the c. The equation that we're going to look at here is x y double prime plus 3y prime plus xy is equal to 0. This is a matching game. Once we know what a, b, c, and p are, then we can flesh out what this solution is. For that, we just want to compare terms that we have in the equation with the one that we're actually solving here. But notice the first term of the equation we were presented with is y double prime. This one is x y double prime. So by dividing by x, we can obtain that form. And we get y double prime plus 3 over x y prime plus y is equal to 0. The matching game says that whatever is in front of y prime is 1 minus 2a over x. So we immediately know that 3 is equal to 1 minus 2a, and that's going to give us that a is negative 1. Further, whatever the coefficient of y is, it's that big old parenthetic quantity. So 1 is equal to b squared c squared x to the 2c minus 2 plus. Now we already know that a is negative 1, so instead of a squared, I'm going to write down 1 minus p squared c squared over x squared. And we match up terms on the left with terms on the right. On the right, we have one term that has an x squared in the denominator. On the left, we don't. That tells me that 1 minus p squared c squared is equal to 0, so that p squared c squared is equal to 1. On the left, I only have 1, a constant term, and on the right, I do have a term that has x to the 2c minus 2. There's a coefficient in front of it. But if there's no x on the left, then that means that 2c minus 2 must equal 0. That gives me that c is equal to 1. Using that, and the fact that p squared c squared equals 1 tells me that p is equal to 1. And so p is 1 because we were told, I didn't say it, that p is not negative. All right, we've got values for a, p, and c, and now we need a value for b. Well, in that term where we had x to the 2c minus 2, the coefficient is b squared c squared. Since on the left side of the equation, our constant is 1, we have that b squared c squared is equal to 1. And since c is 1, we get that b is equal to 1. That rounds out our constants, and so we can write down our solution. Y is equal to x to the negative 1 times the quantity of c1 j1 of x plus c2 y1 of x. That's as much work as we're going to do in this lesson, but I do want to round it out with something called Legendre polynomials. We have a form of differential equation. It is 1 minus x squared, that quantity, times y double prime, minus 2xy prime plus n times the quantity of n plus 1 y is equal to 0. This is something called Legendre's equation of order n. And notice when we were looking at Bessel's equation of order nu, Legendre's equation of order n, those are numbers that are showing up in the differential equation, but these are both second order differential equations. Anyway, the coefficient of the y double prime term is 1 minus x squared. So x equals 0 does not zero out that coefficient. So x equals 0 is an ordinary point. So starting with our basic form, y equals the sum as k goes from 0 to infinity, c sub k x to the k, and differentiating a couple of times, getting common exponents, and making indices match, we end up with a recurrence relation. C sub j plus 2 is equal to negative n plus j times n plus j plus 1, all divided by j plus 2 times j plus 1, c sub j, where j takes on values 2, 3, 4, etc. And writing down a few of these coefficients, I just wrote c2, c4, c3, and c5. Because of that n minus j in the numerator, eventually, if n is even, then the even subscripts will zero out eventually. If n is odd, then the odd subscripts will zero out eventually. If n is 0, then c sub 0 is 1. What I'm giving you are traditional values for the c sub I. If n is an even number, 2, 4, 6, then c sub 0 has an expression negative 1 to the n over 2 times 1 times 3 all the way up to n minus 1 divided by 2 times 4 times n. And then we have similar expressions when n is odd. The punchline here is, for each value of n, what we end up with is something called a Legendre polynomial of order n. And I've listed 6 Legendre polynomials here. P sub 0 of x is equal to 1. What that means is, if our equation that I had read before has a 1 in place of n here, then the solution is 1. If in place of n in that equation we have, say, a 4, then the solution would be a Legendre polynomial of order 4, which is p sub 4 of x is 1/8 times the quantity of 35x to the 4th minus 30x squared plus 3. They come from traditional values for the coefficients. Interestingly, though, if you've seen linear algebra, then you know that, say, P2 is the set of polynomials degree 2 or less. And if you take the standard basis for P sub n and then use the Gram-Schmidt process using the integral inner product from -1 to 1 to get an orthogonal basis, and then scale the resulting polynomials so that when x is 1, the answer is 1, then you duplicate Legendre polynomials. I know, it's an interesting area of overlap.